So after these considerations about reliability, I would like to do the remaining part of our section building a protection scheme. That means look at the required redundancy and backup level. And the leading idea in this context is always what happens if one protection relay doesn't work as desired. That can mean you have a failure of a protection relay, of wiring, of the circuit breaker, and whatever. Then the protection scheme must be designed in a way that another relay takes over this responsibility. And there are different concepts to do that. Let's look at this simple installation. We have a line with an indicated short circuit. We have a protection on both ends, and we have different options to do a backup or a redundancy in this context. And the simplest thing is you just duplicate the protection. That means instead of installing one protection on both sides, you install two protections on both sides. And now the first question in this context is, what are you going to do with the trip signals? Can both trip individually? That means will the breaker trip if one of these two trip? Or do you make a 2 out of 2 logic? That means you will only trip the breaker if both give a trip signal. That is again this discussion about dependability and security. But state of the art in this context is both relays or both protection schemes are independent. That means both relays can trip. That means you can even take one of the two protections temporarily out of service for maintenance or some changes. Then the other one will remain in operation, and if there is a short circuit, it will trip. This can be two identical relays, for instance, two distance relays. Some people say, I don't trust a manufacturer, I take two manufacturers. In the early days, people said, I have one digital relay and one old-fashioned one, electronic or electromechanic even. But nowadays, we have more and more applications where we have communication available, and that gives us the possibility to install, for instance, a distance relay and a line differential relay in parallel. So that is the concept that's called main 1, main 2 concept. You can imagine that is the biggest investment, and you will only do that normally in transmission systems. You will normally not do that in a distribution system. I would just like to add one command in this context. We also offer relays where you have a distance relay and a line differential relay in one box. That gives also some redundancy, but that is not what is required here. Because if distance and line differential are in one box, if this box fails, there's nothing left. That means if you have a main 1 and main 2 concept, you need really two separate relays. But nevertheless, you can say, okay, one of these two relays is, for instance, a relay which has a line differential and a distance on board. And for instance, if the line differential goes out of operation because you have a communication problem, then it activates automatically the distance protection. So you have different options there. Duplication of protection, main 1 and main 2. And that, of course, gives the maximum on redundancy. Even if one relay fails, you still have a full selective fast tripping. But you also have the maximum on investment. The next step would be a bit simpler. Let's take the same example here, the line. And let's now assume you have a line differential protection here. And the line differential protection, it needs communication between two ends. And if this communication fails, the line differential is dead. And for that reason, it makes, for instance, sense to install in parallel to the line differential protection an overcurrent protection as a backup. There you also have two devices, but it's a much simpler thing as having two full-blown distance protection schemes there. That is a thing which you could, for instance, find typically in a distribution system. That is called main protection with local backup. That means you have one backup device installed locally, and in case now the differential protection fails, you have to trip this fault with overcurrent protection. And we will see overcurrent protection tends to have a bit longer tripping times. You may also have some selectivity issues here. So the quality of the protection is a bit lower in case of a backup situation. And the last thing I would like to mention here is the so-called remote backup. Imagine you again have the same situation, a line with two distance relays or two overcurrent relays on both sides. And then we can make a tricky design, and that really saves money because you don't have to install separate devices for backup. You can parameterize, or you can design the protection concept of the previous line or of the next line in a way that it also looks into your line. That means in case the center protection relay fails and you have a fault on that line, then the left side relay will also see that fault, will see, no, yeah, I see a fault, but it's not on my line. I will not, first of all, not react fast on it. But then if the fault is still there after some time, it will say, okay, this looks like a backup case now. Normally, the fault should be cleared in a pretty short time. If the fault is not cleared, it looks like a backup, I will trip. That means at least the fault is cleared. That's the good thing. The bad thing is the tripping in this backup case is done a bit slower because you have to wait. And it's also not full selectivity because you lose not only the line with the fault, you lose also, in this case, the line on the left-hand side. But the fault is cleared. And that is a thing you find all over the different voltage levels in systems where you do protection with overcurrent and distance relays. We always use this concept of remote backup. It gives you a backup without installing additional relays, but you must have in mind, in case of a backup, you will have a delayed tripping, and you will also have reduced selectivity. That means you take into account some deficits concerning trip time and selectivity. Here you see again the comparison. Duplication means two independent systems operate in parallel, and the other one was main and backup protection. And there we accept some limitations in speed and selectivity in case of the backup situation. And also here you can again see that is the economic constraints. Economic constraints bring you in a situation that you accept additional risk. Well, you have reduced selectivity, longer tripping times to save some money. But it's state of the art to do that. And important rule behind that, in all cases, you must think about which device does the backup in case of a missing operation. That's always the idea behind it. So now, finally, I would like to look into a few examples just to show how these protection concepts look like. And before we do that, I would like to show this table. The problem if you draw these overview diagrams about protection concepts, you would normally have to write a lot of long words, distance protection, overcurrent protection, synchro check, and whatever. And that makes the diagram a bit confusing. And for that reason, we often use these so-called ANSI numbers for protection function. The idea is very simple. You list all protection functions we have and you assign a number to it. And protection engineers normally know that. That means if you wake up a protection engineer at night at 3 o'clock and ask him what is 21, he will tell you distance protection. Very clear. So that's at least the main numbers are known, and they make these diagrams a bit easier. So you see here a lot of numbers. A little bit the disadvantage is that these concepts are sometimes not really unique. They are different dialects of these numbers, but I think they are useful. You sometimes find the letter N behind a number, then it's a function which reacts on earth fault or which is tuned for earth faults. We also have NS, the lowercase s means sensitive. And we also have some functions where we don't have a number, like you see there the PMU, phasor measurement unit, the synchro phase measurement, or the FL, fault locator, where we measure the distance to the faults. So that are some newer developments where people didn't assign the number. So these numbers are often used in the diagrams. And now let's have a look at the example. The first example here is a simple, or it's not that simple, it's a medium voltage feeder protection. So you see on the left side, on the top, the 2 bus bars. And then down you have the feeder. You have 2 isolators where you can connect the feeder to one of the 2 bus bars or even to both bus bars. Then you have the circuit breaker, you have the line side isolator, then you have the current transformer, the line side voltage transformer, and in this case we also have a voltage transformer on the bus bar, which we, for instance, need to have a synchro check functionality. So, and all these things are connected to the device. Now remember, the first step is we must think about what is the main protection function. And in this case, we have a medium voltage feeder protection. So typically you apply overcurrent protection there. You see here the 3 functions we are going to use in this case, the 50 and the 51. Depends on whether we use definite time or inverse time. Remember, definite time overcurrent is the overcurrent with the stepped characteristic. Inverse time is the relay with the time-dependent trip delay. And in this case, we also have a directional overcurrent protection. We will hear in the following selectivity chapter a bit more about what is the benefit of installing a directional overcurrent protection. So that is the main protection, short circuit protection. Then in this case, you see we have added some other blocks here. In this case, we have 5 additional functions. First of all is a switch onto fault function. That is also a functionality I didn't explain up to now. What does switch onto fault mean? As I already described, you often have some delays. You need in overcurrent protection delays to get selectivity. That means especially at the beginning of the feeders you have long delay times. And this particular function addresses the situation where you have the feeder, the whole feeder out of operation, and now you reconnect the feeder and somebody forgot to remove an earthing switch or whatever. That means you have still earthing in the feeder, you close the breaker, that means you connect the part of the system where still earthing in there to the bus bar with nominal voltage. And that means in the moment where you close the breaker, you directly see a fault. And for this particular situation, we use a so-called switch onto fault function. That means the protection relay knows I'm now closing the breaker, and if at the same moment a fault occurs, it knows it doesn't make any sense to activate delay time to wait for 600 milliseconds. The fault, the short circuit it sees is a result of closing the breaker and it directly opens. That means this switch onto fault function, soft sounds a little bit strange, the switch onto fault function gives you a fast tripping in this particular situation. FL is the fault locator, 25 is the synchro check, where we assume it is used here. It requires two voltage transformers, one on the line side and one on the bus bar side. We have a 50 BF, means breaker failure, and in this case we also have auto reclosing function because we assume it is an overhead line. That means you find somewhere here also the 79, which is the number for auto reclosing. And then in this case we also have some control logic included there. That means you see here additional some control functions, some logic, maybe interlocking logic for the control of the breaker. So this would be an example for a medium voltage feeder. If we come to high voltage, I can show this example. We have here again a very simple feeder. We have a bus bar. In this case, we have not that much control available in the relay. That means we run the relay as a pure protection and assume that the control function is somehow in a separate device. That means we have connected here only the circuit breaker. We have a current transformer. We have a line side voltage transformer, and we also have a bus side voltage transformer. On the right hand side, I again list the protection functions of these three steps. The main protection function in this case, it's a transmission line, is the 21. It's a distance protection. That means you see the 21 hidden, although it's the main function, it's hidden amongst these other blocks. And then in addition to the 21, we have a number of additional functions. We have a backup overcurrent. What does backup mean in this case? In distance protection, you have the situation that the distance function needs the voltage measurement. Now, because we have to calculate the impedance, we have to divide the voltage by the current to calculate the impedance. The voltage measurement inputs are connected to a voltage transformer, in this case the line side voltage transformer, and now you assume that for any reason you have a short circuit in these wiring there between the relay and the voltage transformer. You make a short circuit there for whatever reason, and that means suddenly the relay loses the voltage because you have an MCB there and that will trip the voltage input, and then you suddenly see zero voltage. And now the situation is zero voltage means to calculate the impedance, you divide zero by a current, and the result is zero. That means you measure the impedance zero, and that would trip. And it doesn't make sense to trip because we have a short circuit, but not on the line. It's a short circuit just in the wiring. And for that reason, protection relays have typically a detection function which detects this situation. That means it detects a suddenly failing measuring voltage and then automatically blocks the distance protection. If you wouldn't do anything, the distance protection would trip in advance. That means this must be a very fast detection function, and also it must not overreact. That is called backup overcurrent protection. That means if this situation occurs, the distance protection is blocked. As a backup, we run the whole system only with overcurrent protection. If we don't like that, we take the main 1, main 2 concept. If we don't want to do the investment, we must accept limitations in tripping time and selectivity by using backup overcurrent. Then we have a ground fault protection here. The reason there is, I mentioned it already, we have normally in transmission, or we have always in transmission systems where the star points are grounded. That means distance protection will react on phase to ground faults, but it has limitations in sensitivity. We will see that in the following videos. We can only detect faults up to a certain fault resistance, and if we want to be more sensitive, we must have special functions which are tuned to detect these ground faults. And in this case, it is a 67N that is an overcurrent, directional overcurrent, which is tuned for ground fault. Then you also see switch onto fault. It's called here a little bit different. 50 HS, high speed. We have under voltage, over voltage, frequency, and we also have here the power swing detection and tripping. Remember, the power swing function has 2 possibilities. It can either be used to detect the power swing and block the distance protection, that it doesn't make wrong trips, or we can use the power swing function for dedicated tripping. And then as additional functions, we have the fault locator, we have the synchro check, breaker failure protection, auto reclosing, and teleprotection. You see here the teleprotection is a function which is nearly always or very often used with distance protection, but it also requires communication to the other end. And for that reason, you see here on the left bottom, you see communication links where the teleprotection function 85 communicates with the relay on the other end of the line. So that was an example for transmission line protection, and the last example refers to transformer protection. For bigger transformer, standard main protection is the transformer differential protection. It is called here on the right hand side 87T. 87 is the standard number for differential protection, and the T means we have here a differential protection in use for a transformer. And then we have 2 additional functions. The 49 is the overload protection, which is a standard thing for a transformer. Avoids thermal overloads, avoids heating up of the transformer. In this case, just based on the current measurement. Otherwise, we would also need a temperature sensor in the transformer or several temperature sensors in the transformer. And we have 50 and 51, which is a backup. And also here in this case, as we have the main short circuit protection is done with the 87T, the faults in the transformer are detected with 87 with a differential. The overcurrent here is mainly used as a remote backup for the following lines. I didn't explicitly mention this thing in the previous two examples. There we had an overcurrent and a distance example, and in these cases you automatically have the backup in terms of a remote backup. That means you actually don't really have to think about backup because it's automatically there. You only have to think about backup when you calculate the settings. Here in the differential protection itself is not able to do a remote backup. Differential protection only looks at its own device, in this case the transformer, and whatever happens outside, it will not react on that. That means if we want to have a backup protection in a transformer protection relay, which reacts on this backup case, if there is a fault on the next line where the protection fails, we must install separate functions for that, and this is in this case the backup overcurrent, in this case 50 and the 51. This was the last example, so we have now a few ideas how we compile a protection scheme, what ideas are required to set up a protection scheme. And in the next series of videos I will explain a bit how do we achieve selectivities by selecting proper settings. In the devices we will discuss that for overcurrent protection, and separately, that's a bit a longer discussion, also for distance protection.